Okay, this video begins the second part of chapter 6. In the second part, I'm going to be naming binary molecular compounds. These compounds are formed by two nonmetal elements or by a metalloid and nonmetal pair. When you're naming the binary compound has got four components to its name. So I mean the binary molecular compound. There is a prefix, there's the element name, and this essentially describes the first element. The prefix tells you the number of atoms in the first element. Then the element name is how you name the first element. The second element, you will also use a prefix to describe the number of atoms. And this time you use the anion name. Okay, so they say that here in so many words: prefix, element, prefix, anion. This is the template for naming molecular compounds, and that's how you can identify them. Remember that molecular compounds, so this is a quick recap. Molecular compounds, when you're looking at them, you can identify them because the first element is a nonmetal. Okay? And for the most part, it's a nonmetal that is not hydrogen, but in some cases, as long as it's not an acid, for example, in water, it's a nonmetal that is hydrogen. Okay? So we look at the compound, look at the first element, and we ask ourselves, is the first element a nonmetal? If the answer is yes, then most likely your compound is molecular. Okay, remember, the format is prefix, element name, and this is how you would name the first element, and then prefix, anion name. That is how you will name the second element. And remember, this is called binary. Binary just means the molecular compound is composed of two elements. Okay? Okay, so how do we get the prefix names? Remember, these prefix or prefixes represent the number of elements. So here is the number, and this is the prefix used. For number 1, we use the prefix mono. For number 2, we use the prefix di. For number 3, we use the prefix tri. For number 4, we use the prefix tetra. For number 5, we use the prefix penta. For number 6, prefix hexa. Number 7, prefix hepta. What about septa, like in September? No, it's hepta. Don't even, Number 8, we use octa. Number 9, we use nona. And number 10, we use deca, as in decade is 10 years, right? Okay, these are the prefixes you use to describe the number of atoms of the elements in the whole compound. Okay, now to expand on the rule, you can use all the prefixes for the first element except for mono. So I usually write here prefix and I put mono and I cross this out. You cannot use mono to describe the first element if you have one. So for example, if you have N and O, no, where you have one nitrogen and one oxygen, you can use mono to describe the oxygen, but you cannot use mono to describe the nitrogen. Why? That's just a rule. The mono is implied. So when you look at a molecular compound's name and the first prefix is missing, what is implied there is you only have one of that first element because the missing prefix or the silent prefix is mono. It's not written, it's implied. It is known amongst the people in a crowd. Okay, so how would I name this compound here? NO. I will skip the first prefix, write the element name for the first element, which will be nitrogen, and then use the prefix for the second element. You have to use a prefix, which will be mono, and then name the oxygen like an anion, oxide, okay? There is another rule I need to add here. Between the second prefix and the anion, if the second prefix has a word, the prefix name, that ends with an A or an O, And then the anion is, say, oxygen. So it has to be oxide like this, oxide. You consolidate the letters. So the O and this O become one O. Essentially, the oxide name remains, but the last letter of the prefix gets dropped off. So we don't have oxide or oxide, we just have oxide. And we don't have oxide, we just have oxide. Okay. If you're wondering what in the world just happened, let me break this down by adding another page. As a student, I went through all those emotional high and lows that one goes through in chemistry. And if you're not going through that, you are unique, or you've already taken this class, okay? Because you're like, what in the world? Why is that necessary? Let's say we have pentaoxide, okay? A scenario where we're describing penta is 5 oxygens. So we have the first element, whatever it is, we don't care about it. We're describing pentaoxide. We don't write it as pentaoxide. This gets written as pentoxide. Why? That's the rule. If you have a molecular compound that ends with, let's see, 1 oxygen, instead of writing monoxide, you're going to write monoxide. And so when I was a student, I was like, I'm not going to remember this, but I do know about a gas called carbon monoxide, which we call carbon monoxide, not carbon monoxide, right? And so I use that as a way to remember the rules, okay? So let's talk about carbon monoxide, CO. This is the gas that's produced whenever you have a combustion reaction, a reaction in which gasoline or some kind of fuel is burning oxygen, but not enough oxygen. And so carbon monoxide is made unintentionally. Okay, how do I name this? First elements. Remember, you have the prefix. You have the element name. You have the prefix. You have the anion name. So how do I name this, right? This is the anion for the second one. Prefix. I like to write mono and then cross it out just to say we don't use mono. First element, carbon. Second prefix, mono. Name of anion, oxide. Consolidate, monoxide. Name of this molecule, carbon monoxide. Did I tell you this chapter was about systematic naming? Yes, systematic as in there is a process. It's not just naming, right? So every time we name carbon monoxide, we're actually using the systematic name of the chemical. So while we're here, let's go ahead and name these chemicals we had here systematically: water and ammonia. Let me use a systematic name to name them. H2O, commonly known as water, is actually 2 hydrogens, right? So dihydrogen, 1 oxygen, monoxide, versus monoxide, consolidate, monoxide. The O in the oxide swallows the other O, so you don't see it, right? You can look at it that way. It's just not there. Okay, what about NH3, commonly known as ammonia? Ammonia, the chemical you smell in Windex. This is, you have 1 hydrogen, 1 nitrogen, right? Remember, the 1 is left out. If you want, you can write it, but you got to cross it out because we leave it out. Nitrogen. We got 3 trihydride. Nitrogen trihydride. Not mononitrogen, just nitrogen trihydride. Okay. And then dihydrogen monoxide. Okay. What is the summary of writing this rule? Prefixes are only used in molecular compounds. Only. Okay, so when I was going over the lab video yesterday, you noticed that when I was looking for a molecular compound, I went ahead and I was looking for the prefix. And where was I looking for the prefix at? I was looking for the prefix in this before the second element. Why wasn't I looking for it here? Because remember, if the prefix is mono, it's left out. So the first element can be good, but it's not the best place to look for the prefix. Look for the prefix in the second part of the name. And when you find it, most likely, like a 95% chance that molecule is or the compound is a molecule, okay? Because the second part of the name has to have a prefix. That's mandatory. And so here we see that table. I just passed that table right here. And of course, we named this already. If I want to name this here, be carbon dioxide. We know that, 2 oxygens. Okay, let's go ahead and name this right here. Oh, I think I already have these here. Dinitrogen, right? 2 nitrogens. I feel like of all the nomenclature, this is the easiest. 2 nitrogens, right? Pentasulfide. Penta is 5 sulfurs. That talks about that. Tetrasilicon. Silicon 4 hexahydride. H6, right? Iodine 1 heptafluoride. F7. Oh, then you have the name here. So here they give you the formula, they ask you for the name. Tetraiodine nonoxide. So you remember, this was nona, right? And then oxide. Then the O from the oxide swallowed up the A. So we have nonoxide, like nonoxide. Okay, tribromine, 3 bromines, oxide. Why did they use these? But remember, 8 is octa and then oxide once again. The O from the oxide swallows up the A. And here we have phosphorus, that means 1 phosphorus, pentafluoride, 5 fluorides, okay? Okay, so we have essentially seen ionic A's, ionic B's. We have now seen acids. We're now moving on to, we're now moving on to acids, okay? So acids is the last section in the nomenclature. With the acids, first of all, they define it. An acid is any substance that yields a hydronium ion in aqueous solution. So here's the thing, back step, okay? There's certain chemicals that can be acids, but they become acids when they are dissolved in water. So when they're not dissolved in water, they have a different property, they act a different way. But when they get in water, all of a sudden they have these acidic properties. And that's why it's important to define the acid inside an aqueous solution, meaning water. Okay, an example of that is HCl. HCl is usually a gas. When you dissolve it in water, H2S is an example of another one. Let me talk about that one. H2S is a gas. You dissolve this in water and it becomes H2S aqueous. All of a sudden, it's an acid. But how do we know it's an acid though? What defines an acid? Because in chemistry, there's certain characteristics you're looking for. You're always judging. And in the world of chemistry, that's appropriate. You're judging before you name or you assign, a category. What defines an acid? If the chemical or the substance is able to yield hydronium. What's hydronium? This chemical here is hydronium. Sometimes they use the species of the chemical H+, hydrogen ion, or hydronium, okay? Oops, sorry, I wrote water, hydronium. Well, in the world of chemistry, these chemicals are the same. H+ is the same thing as H3O. You're wondering, wait, the chemicals are different though. Okay, let me take a step back and break this down like this. Hydrogen ion is essentially hydrogen ion. But hydrogen ion can combine with water. And essentially, so what I'm trying to say here is, when hydrogen ion gets with water, it forms hydronium ion. Okay? So hydrogen ion by itself behaves just like hydronium ion, because hydronium ion is essentially hydrogen ion in water. Okay, so all this is to say, if you have, what does this have to do with naming? You're probably asking, because I would ask that as a student. Like, we're getting lost here. Come back, focus. What does this have to do with naming? When you have a chemical like HCl or H2S or H2SO4, what do these all have in common? They all have a hydrogen in the formula that can be released to form hydrogen ion. What does the hydrogen ion then do? The hydrogen ion doesn't want to remain single like that. It gets combined with water to form hydronium ion. When hydronium ion is formed, we have an acid. So we judge the chemical based on what it's able to do when it gets in water. So when we look at this chemical here, we're like, wait, look at the first element. Okay, I'm looking at this. Is it a hydrogen? Yes. Is it water? No. This is an acid. Look at the first element here. Looking, is it an acid? Well, sorry, is it water? No, it's not H2O. Okay, is the first element and hydrogen? Yes, I went the wrong order, right? Is the first element a hydrogen? Yes. Is it water? No, this is an acid. Look at the third element, okay? I got this all messed up. Look at the third compound, but look at the first element in the third compound, that's hydrogen. Is this water? The answer is no. Then this is most likely an acid. So what is the takeaway in all of this blah, blah? Let me try to give you guys the bottom line. The bottom line is this. If the molecular compound has H as its first element, it is an acid. So of course the caveat here is as long as it's not water, because water is water, H2O is water, then that compound is an acid. At you guys' level, we will leave it that simple, because when we get to higher level, like upper level chemistry classes, they don't put H in the beginning. It's all the way in the end. And remember this, the compound has to, the compound has to have H as its first element. In upper level chemistry classes, they put the H at the end. So the rule there is different. The rule there is the first element the H or is the last element the H? We're kind of looking all over the place. Where is the H, right? But the H being the first element signifies the ability to form a hydronium ion, which qualifies, right? We're trying to qualify before we judge it. Qualify that substance to be an acid. Okay, so now we move on. So it shows you here, HCl has an H and it's not water. HCl can combine with water to form hydronium ion. Hydronium ion makes HCl an acid. So HCl is therefore an acid. Okay, so now that we've done all that, we still haven't named it, y'all. We still haven't named. Okay, with the acids, there are two main types of acids. One is called a binary acid. We're seeing the word binary again. Binary stands for two. This is an acid made up of two elements. Remember, the acid is identified by the hydrogen ion or the hydrogen being the first element. Binary Binary acids identify because they have hydrogen and some other non-metal. Okay, so here's our hydrogen identified, and then we just left the second non-metal ambiguous, X. It can be anything. Okay, so here we have some other random non-metal, and together they make the binary acid. Okay, oxy acids, on the other hand, are named oxy acid to highlight the presence of oxygen. So we kind of have two categories: binary acid, oxy acids. Oxy acids would then have a minimum of 3 elements. The first one, of course, being hydrogen, the identifier of the acid. And then somewhere in there, you have oxygen and the other nonmetal. So I would say the most common format of the way it's written is hydrogen first, the other nonmetal, then oxygen. It's commonly written this way. For example, H2SO4. You have 2 hydrogens, acid, the other nonmetal, and then the oxygen. So I would say that, that's probably the more common format. You have 3 different types of nonmetals. This is called an oxy acid because of the presence of the oxygen. The oxygen kind of overshadows the behavior, okay? Ergo, the oxy acids. So in the acids, two categories, binary acids and oxy acids. Okay, like it says right here, when you're naming the binary acid has got three components to its name. Let me say four, okay? Four components to its name. Hydro. So all binary acids begin with hydro. And then you have the stem component. And then you have ic. Then you have acid. So let me highlight the part that's different. Only the stem part is different from one binary acid to another. The rest of these parts right here are exactly the same. I wanted to relate this to people, but it's kind of like people in the same immediate family, immediate family, have the same last name, right? And so you can tell from their last name where they're from. Kind of. Only in people that say, don't stereotype, don't judge. But with elements, that's exactly what you must do. You must stereotype and you must judge unless their behavior tells you otherwise, right? And so we're looking over here and let's see. All binary acids have this format. All binary acids will start with the word or the prefix hydro, and then the stem word, and then ic acid, okay? So I do have acid exceptions right here, okay? Remember how we learned the stem words earlier and I had a little table for y'all? Well, when it comes to sulfur, you have to modify these stem words. These are exceptions. So what I mean is, you probably remember from before, I said the stem word for sulfur was sulf, right? When it comes to acid, we can't use sulfur anymore. That's just how they name it. It's not sulf anymore. It's now sulfur. It has kind of graduated and elongated. And then before, phosphorus was phosp, right? Now we can't use phosp anymore in this section. We have to use, so for sulf, we have to use sulfur. For phos, we have to use phosphor. I'm just giving y'all a moment as I'm taking a moment, because when I read this, it brings up some feelings inside of me, some kind of feeling, you know? But you have to use phosphor because I'm like, y'all, why can't we just use phos? We already kind of made peace with these prefixes. No, they changed them. Why? I didn't get to have a say. I wasn't even born when these were being named, okay? Okay, so phosphor. Other than that, so remember, the stem word you're using here, these 10 words are for the other nonmetal, not for hydro. The hydro part was already represented here. Hydrogen was represented in hydro. The other nonmetal, you use its stem word and then add the part ic acid. So we have some practice problems here. I already had these present, so I don't have to think and go, let me think of something. I already had these pre-made, ready for us to work on them. Okay. Okay. Am I using the right? Yeah. Okay. Let's go ahead and do this. So I know the stem word for S is sulfur, right? Since it's a binary acid, I have to start with hydro. So since I know they all start with hydro, why not write hydro all over it? Because they're all going to start with hydro anyway, right? Regardless of what the other element is. Oh, hydro. It will all start with hydro. And then hydro. So a quarter of the name is done, okay? And I know this part here, the name is the part that's different. So I'm gonna at least fix for the stem part, but I know that they will all have ic, 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 ic. And they'll all end with the word acid, acid, acid. They all have this part in common. So I'm deliberately writing this way to make a point so that you can see how this is going to work out. Okay, so the part I'm going to fill in is this part right here. And remember, this part goes with the other nonmetal. So the stem word I use for this nonmetal is going to be sulfur. So it's going to be hydrosulfuric acid. Let me move this closer. Okay. And then this is the same one we used before. Same stem word, right? Fluor, hydrofluoric acid. And then this part, oops, I'm clicking on the wrong part. Selen. So hydroselenic acid. Let me move these closer so they look like one word. I was trying to make a point. That's why I wrote those ahead of time. And then let's see. What is this? Phosphor. Hydrophosphoric acid. Brom. I'll erase that part. Brom is the stem word for Br. So hydrobromic acid. And then iod is the stem word for I. So hydroiodic acid. Okay. So hydrosulfuric acid, hydrofluoric acid, hydroselenic acid, based on this hydrophosphoric acid, hydrobromic acid, hydroiodic acid. Okay, remember, hydro reminds you it's binary. Okay. So while we are here, because in your lab work, you're supposed to actually create the acids. I can do this. I'll do this right here. Let me show you how I make the formulas. Okay. I start with, since all the acids have to have a hydrogen ion, I write the hydrogen ion. Okay. And then I write the sulfur ion, which is the sulfide. Then I crisscross them to get this formula. Okay. Now, if you're very attentive, you probably are like, wait, hold up a second. Didn't you just say in the previous chapter, or in this chapter, in this video too, that acids are molecular compounds? Yes, I did. They're under molecular compounds, correct. Why are you using ionic though? The ionic crisscross. Why are you using ions to make a molecular compound? Because the way they get together is not the way they behave when they're in water. They get together by exchanging ions, right? Crisscross. But once they get together and they get in water, they act differently. Now they're acting like an acid, like a molecular compound. That's just how they are. Okay. H plus, F minus, crisscross, and we get this. H plus, Se2 minus, crisscross, and you get that. H plus, P3 minus, crisscross, and you get that. H plus, Br minus, crisscross, and you get this. H plus, I minus, crisscross, and you get that. Okay. Let me check to make sure we are recording good. Okay. I just have to check the times when I'm like, I have gone through whole lectures and I forgot to press the record button. Okay. So there are times when, oof. That is the end of a binary acid. Okay. Now we're talking about naming oxy acids. When you're naming oxy acids, apparently there are two types of oxy acids. I know. There is more. When I get done, I'll summarize everything. Two types of oxy acids. And for the oxy acids, you're starting from the oxy anion to the acid, and then you name it. So saying here, in naming the oxy acid, number one, you're going to name the oxy anion first. So if you've forgotten what the oxy anion is, this would be like nitrate, nitrite. The ones that end with ate and the ite, you will name those first. And then once you name those, you will replace the ite part of their name with us acid. I'll work this out so you can see. And then for the other kind of oxyanion, if the oxyanion ends with ATE, you name the oxyanion. If it ends with ATE, only replace the ATE part of their name with ic acid. Feel free at this point if you have to rewind. I hope you're taking notes as you're watching this video, not just listening, because there's a lot of involvement in chemistry required for you to really get this stuff. Okay. So when I was studying this years ago, trying to memorize this, I was pacing back and forth because I noticed for me, I've heard that with certain kids with special needs, they usually do this to kind of help them engage their minds. Is it called steaming or something? I don't know. I don't know names and stuff. I just know what helps me out. When I was struggling to memorize stuff in school, I still do that now. I will pace. Like sitting down doesn't work for me. I have to engage like my brain extra. And so I will walk. And somehow stimulating the bottom of my feet helps me to be more alert. And when it does, it heightens my level of alertness. It helps me to learn. So even though I have bad recall, you're probably wondering, it looks like you're recalling this. The processes I'm using is different for people who regularly recall things. I have to be actively engaged to recall things. If this is not your issue, kudos for you. Okay. But yeah, this is just my issue. I have to be actively involved. So when I'm listening to a lecture like this, I'm taking notes. That's part of me being actively involved as I write. Even if I never read the notes, writing down, having that pencil, that pen, and something tangible to hold on to helps me engage. Even when I'm teaching, moving my hands, it's very important. Even if the camera is not on, my hands are moving because that helps me to be actively engaged. Okay, enough with that. Back to this. STEMite, you name the anion first. So you look at the acid and try to visualize the anion within the acid. Name the anion first. If the anion ends with ITE, replace the ITE with US acid. If the anion you have visualized ends with ATE, after you have named it, replace the ATE with IC acid. Okay, so remember, I becomes US acid, A becomes IC acid, and I'll pace back and forth. US acid. People walking around me saying, you are becoming something else, like you're losing it. I'm like, no, I'm trying to get an A. It looks like I'm losing it, but what you're seeing, you're misinterpreting what's happening here. I'm trying to get an A. Did I get the A? You betcha. Yeah. I becomes US acid. A becomes IC acid. I'm sorry. I get so excited with it. It takes me back to the days of my struggle, yet my victory. Okay. Well, so you want to see this in the acid. You want to see an NO2. Now, in the acid, you won't see the negative sign because acids are compounds and compounds have no charges. So you won't see the negative sign. So what you're looking for in the acid, apart from the H, you're looking for NO2. Okay, so what I'm going to try to tell you is here. Let's make the acid so you can see. So before I start naming this, let's make the acid. Just like before, we're going to crisscross, right? So here's what I'm going to do. Let me follow this. Let me borrow this section here to make the acid. For each of these anions, you're going to add an H plus. Well, how many H pluses? The different anions. The correct number of H plus needed, one for every negative ion. So for right now, I'm borrowing this column, okay? And it says anion name for right now, but guys, I need to borrow this right now and I'll say crisscross because I'm literally using the crisscross method to form the acid, okay? You're crisscrossing all these anions with the H plus because remember all acid starts with H. And then I'm going to write the anion here, okay? And then I'm going to crisscross that so that I can make the acid right here. And then once I do that, I know you're probably thinking this is getting very long. I didn't realize this chapter was so long. It does take a lot to understand this if you don't really get it. But once you get it, is it systematic? Ish. Not as much. C2H3O2 minus CrO42 minus. I'm trying to engage you with the stories of my struggle and to let you know if you're struggling, you're in good company. And look at me after, right? I make it look so easy. No, it was a struggle. Okay, like before, you're crisscrossing this, right, to get the compound. So we end up with HNO2. Okay, so remember, In naming this acid, we are trying to find the anion, the oxyanion, the non-hydrogen part, and we're going to be naming that first. So find the non-hydrogen part, name that first. From the non-hydrogen part, then you get the acid name. I know it's like this, you're just trying to name. It takes a while though, okay? Here, same thing, crisscross, HNO3, crisscross. See the 2 comes down here and then this disappears. H2SO3, crisscross, H2SO4, crisscross, H3SO4, crisscross, HClO, crisscross, HClO2. This is just -1, right? Crisscross, HClO3, crisscross, HClO4, crisscross, HC2H3O2. Let me take a pause here, right? If you're a kind of person who really wants to be engaged in the learning process, which all of y'all should be, right? Like me, I'm always questioning my head. I'm like, wait a minute, hold up a second. Why do you not consolidate this H into those H's? Are they different H's? Yes, they are. They're different H's. This is the only H that can actually be removed. Where these are located, they can't be removed. So these are the hydrogens that make this compound an acid, not those. That's explained in organic chemistry class, not this class, but just know that's why we don't put them together to get C2H4O2. If you were wondering, if you weren't wondering, what I just said was nothing to you, right? Because I'm not the kind of person, I'm like, hold up a second. I want this one here over here with his friends. H2CrO4. Okay, so now that I have built my acids, I want to go ahead and highlight the anion portion that I'm going to be naming, and that will control the name of my acid. This is the part that I will be using to get my stem part, and not only that, the name of the acid. Sorry, y'all, we all congested over here. See, I sound, wait, how do I have this? Excuse me, guys. You know how I talk a lot, and then it's supposed to be H3PO4. You probably saw that and you're like, we hope she figures it out. When I'm going through, I'm always trying to check my work because I know I talk a lot when I'm writing. But imagine me having this video and not talking at all, right? That'll be very weird. Okay, so now I'm done with this column. I can name it what I want to name it appropriately, which is I want to name the ion, right? And maybe you can arrange the column differently. Okay, so this is not going to be the anion name. Remember that list I told you of earlier, the list that was provided for the oxyanions? You want to go back there and find the names of these oxyanions, okay? I happen to have a list in my head now after all that work of pacing back and forth in the hallway. So this is going to be nitrite. This is going to be nitrate, okay? And so remember, the rule is once you name the oxyanion, so this is the oxyanion, okay? You see that it's not just the anion, it's the oxyanion. Same thing with this. This is the oxyanion because it's an anion that has oxygen in it. Once you name it, it says replace the ITE with OUS acid. Okay, so replace this ITE with OUS acid. So I'm going to replace this part. Nitrous acid. I took out the ITE and replaced it with OUS acid. And that's essentially the name of the acid. I'm following the rules. So the ite becomes us acid, right? And then the ate becomes ic acid. So I have nitric acid. This is replaced, this is replaced. So this is like the new nitric acid. I replaced the ATE. Okay, so this would be sulfite, sulfate. Now with this one, remember there's a caveat to the sulfur, right? I know you're like, no, why? I was doing so well. Yeah, but we gotta go through this, guys. We gotta go through this stages in life. You gotta go through the hard and the easier. Remember, when you're dealing with sulfur in the acid name, you have to use the elongated form. So you can't just write sulfus and sulfic. You have to use sulfur and then do the OUS and then sulfur and then do the OU. Oh, sorry, and I'm not getting caught up in the process in a bad way. Do the sulfur and then add the OUS. Do the sulfur and then add the ic. So we had to elongate the sulf to sulfur in the acid, add the OUS, add the ic, and then the word acid. So all of these are added. And then I'll say this word here got elongated, and then this word here got elongated. You know what I'm saying? It went from sulf to sulfur, and here we have this OUS acid, ic acid. Okay. And then same thing with phosphate, right? I only had one, or could I have two? That's okay, y'all. This is doing the most. Phosphate. Remember, with phosphorus, you have to change this to phosphor. And then ATE gets replaced by ic acid. And we get phosphoric acid. Okay, oops, wrong part. This part got replaced. And this top part got elongated, if you're wondering. Okay. Then here, let's see, I changed this part, ATE with ic acid. So here I have, oh, let's remember these ones here. I know there's so many stars. Now you're like, you have stars everywhere. I'm sorry. Okay, remember this was chlorite. This was chlorate. And then one more oxygen than chlorate is perchlorate. Perchlorate. And then one less oxygen than ite is oops, wrong place. Hypochlorite. Okay, so once I've named all of those, I come over here and replace the hypochlorous acid. Replace the ite with OUS acid. Okay, this is right here, this is right here, ite, 8, that shall be replaced. And then chlorous acid. This whole part is new. Then chloric acid. That whole part is new. And then perchloric acid. It requires a certain level of discipline, a certain level of sleep, a certain level of food to really focus on all these rules. We got two more, guys, two more, and then we're done with these rules and I can summarize it, okay? Oh, I forgot. We have to do the one with the water, right? Okay, almost forgot. Acetate. I think this is chromate. Let me make sure. I think it's chromate. I have to go back and go back. Okay, you know what? So you guys don't feel dizzy just watching this. Let me scroll here. If you get dizzy. Oh, you know what I realized? It's actually in your lab. I'm looking for the attachment in your lab, not here. My bad. See, this is the issue I have for. Okay, it's not here. I think this is chromate because dichromate is a Cr2O7 2-. Okay, so this part is going to be changed. This part is going to be changed. Let me highlight the parts that are going to be changed. The 8 becomes ic acid, so we have acetic acid. Remember, that's the vinegar. It's actually the common, not the common name, but yeah, the systematic name. And then we have chromic acid because you're replacing the 8 with the ic acid. And here we are, done with this list, guys. We're doing very good. I'm so proud of us, right? So here they have their list. We have done that. Did I do carbonic, carbonate? No, I didn't, but you know what? I can add to the list right here. CO3, 2 minus. This is carbonate. The acid is H2CO3. And it's going to be carbonic acid. 8 got replaced with ic acid. Color over here, color over here. That, y'all, my brain is a wandering brain. It's like, it's hard to box my brain. Just trying to remix everything I'm learning. Okay, so we have essentially named acids. Okay, remember you have binary acids, you have oxy acids, and we have seen all this here. And this is just giving you dialogue about all the acids we've seen so far. They're going to the per, hypo, hydro. I've done all of these already, right? So like I mentioned before, when we're naming this right here, so this is an example of how you're going to be naming stuff. This, they gave you the acid, right? You can reverse crisscross to get the I mean, that's what I'll do, because and now I've memorized, but before I memorize, I like systematic methods because my brain is wired to accept that easier. So what I'll do here, I will reverse crisscross, y'all. So I'll bring this back here. And then this 3 doesn't go back here because these are together. If the 3 did not belong to this group here, there'll be a parenthesis between this, right? Like that, right? But there isn't. So I will bring this back here. I'll bring the 1 back here. And I know H is plus anyways. It's not any other number but H plus. So SO3 2 minus. And then name this. This is sulfite, right? Then replace that with OUS acid. Oh, sorry, elongate it first, my bad. Elongate it first. Sulfite, right? Replace this with OUS acid, and then replace this with sulfur. How about that? Sulfur. So sulfurous acid. Yeah, sulfurous acid. Okay. What about this one here? Recognize this. Split the H plus from the rest of the molecule. Name that perchlorate. Replace 8 with ic acid. No need to elongate this. So you got perchloric acid. This one here, separate this from BrO4 minus. Name this perbromic. Oh no, perbromate first. And then replace the 8 with the ic acid. It becomes perbromic acid. So when you know the systematic way of naming, then when they give you strange looking ones, then you can actually name it, right? So for this one here, okay, we have TeO3, 2 minus. So tellurium is a cousin, long distance cousin, not really. It's in the same group as sulfur, right? Tellurium is the same group as sulfur. So to make the acid, you crisscross H plus with tellurite. This is tellurite. Oh, I forgot to mention this. Let me take a step back. Okay, tellurium is in the same group as sulfur. For that reason, since we know sulfate, replace the Te with O42 minus, replace the S with the Te. If this is sulfate, then this is tellurate, okay? But they have TO3. So if this is sulfite, SO3 2 minus, then this becomes tellurite, TeO3 2 minus. Yeah, this is a tedious process. So when it comes to naming the acid, then the acid that's formed by H combining with this is going to be tellurite. Replace that with OUS acid, tellurous acid. Because they're the same family, same group, they're almost interchangeable. Does that make sense? interchangeable when you're making the formula. Like if you know the formula of SO42 minus, then if you know the formula of sulfate, then you can predict the formula of tellurate because they're in the same group. Their bonding is similar, very similar. Okay. So let's see. I'm not gonna go over all of this because I've already done all of this before. I'm trying to see if there's anything here that's new. I've already shown you guys how to get the ions from the acid, reverse crisscross. Oh, here we're just naming. Okay, so this is kind of like a naming compounds. Okay, so before we go over and name these last few compounds here, wow, they give you all tough compounds. Let me summarize. Okay, so I want to go ahead and summarize here. I want to add a page and summarize. And I want this page to be like that. No, checkered. Okay. What is this box over here? Why is it? Okay. Anyway. So what I want to do here is I want to start with, we're naming compounds, right? I'm going to write shorthand. So this is naming compounds. I'm summarizing what we covered so far. First element. If our first element is a metal, then you want to follow the path to the left. The path to the left leads you to ionic compounds. Remember, ionic compounds are the ones that are made up of metal plus non-metal. The first element is the metal, and that's how you identify it. Okay, the ionic compounds, we have two types, ionic A compounds and ionic B compounds. Okay, ionic A compounds, example here is KCl. The format of nomenclature, the template that helps you is you will have an element name and then you will have an anion name. So they tend to have just two names, element name and anion name. Okay, remember the element name is a group 1. The element name, which is for the first element, which you name as an element, is a group A metal. The second element, which is named as an anion, this is a non-metal. Okay, example of ionic B compound is, example here is FeCl3. With this one here, when you're looking at the template of nomenclature, I'm becoming aware of space and how I'm running out of it. I'm gonna just write this smaller in a little bit. I'm just gonna make it smaller. You're gonna have element, you're gonna have charge, and you're gonna have anion. So when you're looking at the name of two compounds, one being ionic A, the other one being ionic B, you can tell the ionic B from ionic A by looking at the charge. And this is the identifier here, okay? You should recognize the first element as being a group B metal. The second one, of course, would be a non-metal, okay? Now, once again, ionic compounds are recognized as ionic compounds. Why? Most of the time, 90% of the time, the first element is the metal. And that's the identifier that tells you this is ionic compound. And then your next question is it ionic A or ionic B? Ionic A compounds have the metal in group A. Ionic B compounds have the metal in group B. These are the D and the F block mostly. Okay. So let me go ahead and shrink this. Because I need that space. Okay, so let me go ahead and erase that. I need that space on the right. Okay, so on the right, today we covered a situation where your first element is a non-metal. If the first element is a non-metal, So here we have what we call molecular compounds. These are non-metal and non-metal. Remember, the first element, the identifier, is a non-metal. Okay, for this we have regular molecular compound. I say example N2O. The template for naming this, let me try to stick with this. The template for naming this is going to be, of course, prefix. And I write here mono, X out, element, prefix. Oh, I need space. Anion. Okay, how do I make this smaller? I try to make it smaller, but I have a knack for writing really large. There. Okay. And that's how we know. So what is the easiest way to identify a molecular compound? You want to look over here and you see your prefix, and this is what's telling you, right? You're looking for prefixes. Remember, the prefixes are mono, di, tri, tetra, penta, hexa, and all of that stuff. Remember, this is going to be non-metal. And this right here is non-metal. I'm trying to keep with the theme. Okay, so when it comes to your acid, I want to go further down because I need a little bit more space with this. So this is when we say this, I should say down here. So we know what we're about to do with down there, right? Then the next one is going to be acid. Starts with H, most likely it's an acid. And to name acids, I had to come down here because I'm running out of room. Okay, with acids, we have binary acids. Let me write a little bit to the left over here. I need more space. Binary acids. And over here, I have oxy acids. Okay. Binary acid, example HCl. This is my example. The format of nomenclature is hydro, stem, ic acid. The part that really helps us to identify this type of acid is the word hydro. They start with hydro. So this is the part that you're looking for. So I try to highlight the key parts that you're looking for that will help you know this is the chemical you're dealing with. Ionic A compounds are very basic. They're named very basically. You're not seeing, there's no prefix, there's no charge, there is no hydro. Okay. And then of course, yes, they're very basic. With ionic B compounds, you see the charge in parentheses. Remember, the charge is written in Roman numbers, right? So this is going to be in Roman numbers. Molecular compounds, you're seeing prefixes, mono, di, tri. Binary acid, hydro. Oh, not only hydro, and then stem ic. So hydro and then something ic acid. Now with the oxy acids, we have two options here. You have HNO2. So this is going to be stem us acid. Oh, I'm writing the box in the wrong place. I need more room, y'all. I need more room. I feel like the more I'm writing, the less room I'm having. HNO3 stem ic acid. So what is the identifier in this acid here? First of all, you have OUS and you have an ic here. Now you can argue, wait, these both have ics. But what is the obvious thing that's missing here? Missing hydro. So I would say the biggest identifier here is the fact that these names are missing the prefix hydro. I just thought about it. With this one here, these are missing Roman numbers. I'm trying to show you how to identify this a different way, the thought process that you may use. Missing Roman numbers, these are missing the prefix hydro. Okay, stomach acid, stomach acid. This one here is, of course, less oxygen, more oxygen. I know it's like a little cartoon thing over here, but this is the best I could do, y'all, because I'm writing so big and I want to make sure you guys can see it, right? So it continues down here. And so we have essentially named 1, 2, 3, 4, 5, 6 different types of compounds, okay? Then down here, I will come back to this. Down here, I want to just complete the new stuff that we're learning, where they talk about adding water. Yes, water crystallization. I want to finish this part, and then we'll go ahead and go through that part. With water crystallization, all you're doing here is taking an ionic compound. So you have an ionic compound that has water molecules embedded. Embedded is kind of put in, it's chemically combined, embedded in formula, in its formula. Okay. So here we're shown that copper sulfate contains 5 waters in its formula. Okay, so this is how you write it. And this water is a different kind of water. It's different from taking copper sulfate and dumping it in the water. When the copper sulfate was being formed, it took with it 5 water molecules from the atmosphere. So the water molecule, I almost want to say it's part of the DNA, but the chemical doesn't have DNA. But think of atoms being like not really DNA, like cells. Atoms are like cells to the compound. So the 5 waters is like additional cells that got added during the formation of the compound. When you're making copper sulfate, 5 waters got added. And so how do we know the copper sulfate has water, which is called hydrated, right? This is hydrated, meaning when it was being formed, when the copper sulfate was being formed, it took within itself 5 water molecules, versus the one that doesn't have water. This is called anhydrous. It's not dry. It doesn't feel wet. When you see the hydrated copper sulfate, it looks like beautiful blue crystals, kind of like gems, like a tanzanite, not really tanzanite, but kind of like a tanzanite, because tanzanite is more purplish blue, right? Sapphire, something else, aquamarine, yeah. see what I know? I don't know. Hold on. Anyway, it looks more like an aquamarine gem. So it doesn't feel wet, if you're wondering. Hydrated is not the same thing as dissolved in water. Because it's part of the formula, when the copper sulfate is made, it looks, wait, hold on a second, y'all. Okay, so here I actually stopped to kind of show you this stuff. See right here, you have the hydrated copper crystals, copper sulfate crystals. So it doesn't feel wet to the touch. It actually feels dry. But when you heat this up to get the water of crystallization, the one that got incorporated in the structure, to get it out, it goes from having this crystalline shape. These are all still crystals, right? They look very pretty. I mean, when I get them, I'm like, wow, so pretty. Then it goes from that look to this white powder where the structure changes completely just by losing water. So we have hydrated, and then on the right, far right here, we have anhydrous. Okay, so let me go back to the presentation right here. Okay, so how do you get rid of the water molecules? By heating. Just heat it up and it separates. So in your homework, you'll be asked to write the formula for hydrated compounds. Just put the dot in there, and then you will use the prefix to describe the number of water molecules. Now here they do have additional prefixes besides the one we used before, such as hemi. Hemi stands for half. And then of course you have mono, di, tri, tetra. You will use those prefixes to describe the number of water molecules. So this one here, to name this compound, the hydrated compound, I'll go ahead and name it down here. It's copper, copper 2, right? This is a ionic B. copper 2 sulfate. So you need to have that, right? Let me take a step back. I know you're like, wait. Okay. Remember, start with the charge of the anion. This oxy anion is sulfate 2 minus. And since there's nothing here, that means that copper was also 2 plus, right? So you name this as copper 2, and then SO4 2 minus. This is going to be sulfate. That's the name of the anion. And then we have 5 waters, penta. And then the water, you use the term hydrate. And that's essentially how you will name this compound. Copper 2 sulfate pentahydrate. So this is copper 2 sulfate with 5 waters, okay? If it's 1 water, you use mono, and if it's 2, it's di. And if it's half a water molecule, it's going to be hemi. How can you have half a water molecule? That just means that there's 1 water molecule holding 2 separate compounds. So when you're looking at one compound, you're saying, well, this compound only has half of the water molecule. Y'all, I know. You're probably like, what in the world? Okay. So let me try to complete this part here. Here we have, once again, this is just going to be, this is a regular ionic A compound, so you don't have to provide the charge. It's going to be sodium for the first element. And then this is going to be carbonate. And then we have 10 decahydrate, like you see right here. This one right here, down here, we have, oh, you're writing the formula. So nickel 2 plus chloride, Cl minus hexahydrate, 6 waters. So crisscross this, you have NiCl2.6H2O. Okay. And that essentially completes the chapter. Now the rest of this right here, I know I skipped over this, but I already did a lot of work when it came to you guys. I did a lot of work when it came to your lab to help you guys out. But I'm going to go through here, not necessarily in order. I'm going to name this because I'm trying to go from the bottom now to where I left off. So naming this right here. So you see the 3 came from here. So this is going to be iron 3 plus, and then you have this. Go to your list. This is called bicarbonate. So iron 3. I have to use the parentheses because this is ionic B, metal. Let me write properly. Iron 3 bicarbonate or hydrogen carbonate. So iron 3 bicarbonate or hydrogen carbonate. Then we're not going to be going over that part. This is the last part that I have. Oh, I have this part left, and that's it. I'm done with the whole chapter. Okay. Magnesium is ionic A, so I'm going to only have 2 parts. This is ionic B. This is ionic B. And then writing the formula here, aluminum is ionic A. Lead is ionic A, that behaves like ionic B. Potassium is ionic A, okay? So we talked about this yesterday, but since we're here right now, let's get it done. I know it's written down here, but magnesium, you name the first element as magnesium right here. And then this part here, look at that list, the list I gave you. I told you you need to have it next to you so you can actually name this perbromate. This one here has to have 3 parts of the name, including the charge. Iron, the charge comes from down here. You reverse crisscross to get iron 2 plus. So you can name it as iron 2. Then this one here, oh, don't forget the nitrate, right? From here, sorry, not nitrate. This is not nitrate. This is nitrite. Let me go back. This is nitrite, okay? Here we have this, goes back here to 2 plus. So we have copper 2 plus, and this becomes copper 2. Now remember, copper isn't always 2. You can't assume it's 2. And this is IO hypoiodide. Don't worry, the exam will not be this complicated. This is them, they're just stretching you a lot here to make sure you know the rules, right? Aluminum chloride. So you got aluminum. I don't know what all of this is. Aluminum 3 plus chlorite. Chlorite is see, okay, let's see. You have per chlorate, you have chlorate, you have chlorite. See, I told you guys I have to remember the list and then hypochlorite. Okay, there's my list. I got it. Aluminum chlorite. So when you crisscross this, you get aluminum ClO2 and then the 3 down here. And then lead 4 phosphate. What? This? Oh, this came from here. And this is supposed to be chloride. Why do they butcher this? Oh my, and I just copied and pasted it here because once it gets in here, it's a PDF format. In the PowerPoint slide is a picture format. So I have to go and delete what they messed up on. It's a formatting issue. Things move. And this is supposed to maybe be chloride. That's okay. This is chloride. And if it's chloride, if it's aluminum chloride, then this is going to be Al3 plus Cl minus. There's going to be AlCl3. That explains how we got this, because I'm looking at this like this is a mystery, and I got to solve me a mystery. So if it's chlorite, ites and ates have oxygen in them. If it's a chloride, IDE, there's no oxygen. This would be the answer. Okay. So let me go ahead and erase. Oops. Yeah, you can rewind this and watch that part over and over again. So if this is IDE, then that explains how we have AlCl3. If it is chloride, if it's aluminum chloride, then it's going to be AlClO2, 3. Okay, this goes with that. Okay, this is, because yeah, this is a messed up here. And then lead 4 phosphate, lead 4 plus, phosphate is PO4, 3 minus. Put this down here, put that down here, we get lead 3 PO4, 4. That's what happened to this. So lead 4 phosphate, I guess to fix it here, I can fix it right here. I'll just add the PO4, 4 down here, and that fixes that. Okay. Yeah, this slide got messed up really bad. Let me do this here. And then potassium selenite. You got potassium, you got selenite, right? Bring this down here and we get that. So this is correct. Oh, this is just, let me just talk about this real quick and I'll be done. I'm trying to make sure I give this video enough time to encode, because I'm realizing now it's taking hours to encode, to copy over each time. Okay, this is phosphoric acid. Is this showing you that once the acid is formed, the acid loses the hydrogen when it gets in water? It doesn't just dump them all at once. It loses the hydrogen one at a time when it gets in water. So remember, acids have hydrogen and they do have negatively charged anions. So the acids, the hydrogen acid tends, it says hydrogen bearing acids. Acids have hydrogen. Oh, because there's some that don't have hydrogen. We talk about it in the majors class. But in your class, hydrogens have acids. They release these hydrogens in water, these acids, one at a time. So it's showing you, in this case here, phosphoric acid that has 3 hydrogens loses each hydrogen one at a time. And each time it makes an ion, right? And so these ions are separate, they're named separately because they can exist as is. They can release just one and then be like this, or release 2 hydrogens and then be like this, or release all 3 hydrogens and then be without any hydrogen. So this is called dihydrogen phosphate ion. This is hydrogen phosphate ion or phosphate ion. And I think this wraps up the chapter, okay? And I am done.